I tried to do Talent's job. Well, not really. I tried to do a really small part of it. So as we're all aware, BBD is a company built on people. And so we need to find good people. The way that we do that is we get CVs, we send people a test and use that test as a way to filter out people that are good candidates. The problem is that a lot of people get a test and go, no, I don't like tests, I don't want to do this. So what we were trying to do is find a way to prioritize Talent's time so that they can go and find good potential candidates and follow up with those candidates first before they follow up with candidates that are less likely to be good hires. So we're trying to prioritize. So let's have a look at this. Feel free to pause and have a look at a CV, but guess if this CV passed or failed. Well, this one failed. How about this one? This one also failed. What about this one? Well, this one passed. How about this one? Well, this one also passed. What about this one? This one also passed. How about this one? Well, this one failed. So, as we can see, passing judgment is not that easy. Just from looking at the CVs, it's not clear what is there, and then to automate this becomes even harder, as there's no such thing as a standard CV format. So, in case you haven't guessed, I'm going to reach for the buzzword bingo hammer of AI in order to try solve this problem. It makes sense because what we're wanting to do is get a probability of a candidate passing our test. Fits well within the AI domain. So, as we've seen, our data is CVs. In the real world, we've got this really disproportionate split between candidates that are passing and candidates that are failing. Now, AI will learn that and bias any input towards that, where we actually want our AI to learn based off of the features of the CV that it's seeing. So we've curated our data set that we're going to train with so that we've got 50% passing and 50% of our data set failing. We did this just by subsampling all of the failing candidates and using all of the passing candidates. Right, so we've got CVs. CVs are words. Words do not work well with AI, so we need to find a way to convert from language into a numeric input that AI can work well with, particularly machine learning. There's several ways to do this. The first is to just treat it as a bag of words and not pay attention to word order and convert each word to some sort of representation. The next way is also to convert a word to a representation, but take into account word order. The last way of doing this is to go through and extract features from the CV. So, for example, where they went to university, what was the last company they worked at, how long did they work there, and use those features and convert those features to numeric representations to use as an input. So we'll step through all of these approaches and have a look at them. We'll start with the simplest one. So, the first one that we're going to look at is term frequency document inverse frequency, or TF-IDF. You can think of this as a word cloud, where words that carry more information have a higher value, visually larger. So the way that this is done is by looking at a corpus of text. In our case, we've got two here. The quick fox is our first document, and the lazy dog is our second document. And what we're going to do is go through and create a weighting for each word in a document given the context. So if we go through the first document, the quick fox, we look at the word the. It appears once in this document, so our frequency is 1/3, because there's 3 words. The same for the rest of the words. Now we get to the inverse document frequency. What we're going to do here is take the number of documents in the corpus, and then divide it by the number of times the word appears, plus 1, so that we never divide by 0 and run into issues. So, as we can see with the word the, we're dividing 2 by 3, which means that we're going to get a much smaller value for the than quick and fox. So we get more information from the words quick and fox, and we discount the value of the word the. So we've got a way to go from text to numbers. But how do we use these numbers that we've converted our CVs to? Well, we're going to go through several classical approaches because these give us a good indication of what we can expect from our model, and they're also really quick to train, whereas more sophisticated approaches take more and more time. So let's explore a couple of these. We'll start with random forest. So what random forest is a collection of decision trees. And each decision tree gets given a different subset of a CV. So you can think of it, if we've got 3 trees in our forest, the first tree will get the first third of our CV, the second tree will get the second third of our CV, and the last tree will get the last third. And then we get the answer from all 3 trees, and we aggregate these together in a fashion. The reason for doing this is that a decision tree overfits really quickly to training data. So in other words, it works really well on data that it's seen before, but the moment you try to give it something that it hasn't seen, it does really poorly. So by using several trees that are only seeing part of the data, and then voting together a group of weak learners, that overfitting is minimized by the group, because each tree has an influence, and so if one tree overfits and another tree doesn't, as a whole, the model generalizes better. Right, so the next one we're going to look at is Bayesian theory. This is a probability of y happening given the probability of x. So let's step through that so it makes a bit more sense. We've got a sample space. These are all of our CVs that we've got. Then if we go through that sample space, we can go and say, well, what's the probability of getting a word such as PhD? That would be the thin gray sliver, and then the large gray block would be all of the CVs that don't have that word. And then what we're going to do is say, given the probability of the word PhD, what is the probability of the candidate passing? So as we can see here, if they've got a PhD, in this example, they're a lot more likely to pass our test. Whereas if they don't have a PhD, there's still more candidates that are going to come through, but as a percentage of their population, it's a lower percentage. So the next one we'll look at is a support vector machine. So there are a couple of ideas to walk through here. So as you can see on the left, we've got a maximal marginal classifier. Basically, we've got 2 clusters, passing CVs and failing CVs. And what we want to do is divide these clusters with a hyperplane. A hyperplane is just a 1-dimension lower split of the current dimension. So if you've got a number line, it would be a point. If you've got a 2D space like this one, we've got a line through that space. If we've got a 3-dimensional space, we've got a 2D plane. Okay. So the way we get this split is we look at the points that are closest to the edge. We take the distance between those points and we just divide it in half, hence the maximum margin. But we run into an issue over here. It works really well if our clusters are clearly separated, but if there's a bit of overlap between the clusters, it doesn't work as well. So what you do is you move to a soft margin classifier. What this will do is it will look and accept a little bit of inaccuracy as long as the group is better split. So that's what you're seeing on the right-hand side. But there's one more problem to deal with. So as you can see, we might not have clusters that are easily separated by a line, such as a circle within a circle. And we can't split that with a hyperplane. So what we're going to do is we're going to explode the dimensionality of our data. So move from 2D to 3D, up and up and up, until we get a split that we can separate with a hyperplane, or we hit a threshold and we accept our losses. So over here, we can see that when we go from 2D to 3D, there's a clear split and we can fit a hyperplane in between those two. So the next one we're going to look at is a perceptron. This is a foundation for deep learning. Deep learning is just several perceptrons stacked on top of each other. So what we've got over here is an input on the left, x1 through xn. You can think of those x's as the words, word 1, 2, 3, all the way to the end of the CV. What we're going to do is multiply each of those words by a weight, which allows us to learn how important that word is. We're going to sum up all of those importances, and then we're going to put that through an activation function, which is going to take a number that's in a continuous space and force it down to 0 or 1, pass or fail. So this has got to learn somehow, because those weights are going to be random when we start, and we've got to move those weights so that on average, our model is more and more accurate. So how do we do this? This is a process called backpropagation, and gradient descent is the simplest and easiest to explain. Basically, what happens is, for each example, we know the answer that the model gives us at that model state, as well as the true answer. And we can get the difference between these two. So because we got pass and fail, we can go and say The example A gave us a pass from the model, but it was actually a fail from our labels. So we've got a loss of 1. Our next one failed, and our model said that it failed. So we've got a loss of 0 and a total loss of 1. What we can then do is take the derivative of that loss function to give us a gradient. And that gradient is with respect to the weights. We can then adjust the weights so that that gradient is minimized. And so our model will learn over time. And so what you're going to do is walk down from a really high loss function value all the way to a low loss function. And as you do that, the model becomes more and more accurate, giving better predictions. So if we look at this over here, what you're seeing is a whole bunch of these experiments run with all of these different classifiers and different iterations of those using different regression factors. But what we're seeing over here is that on average, they fall about the same point. So we can collapse all of these down and just look at several experiments together. So what we're looking at over here is 9 splits of the same data. So all the same CVs, and all that we're doing is using a different 20% to validate that our model will work in the real world. So if we look at this, the first 3 splits that we've got over here are effectively random. There is no value, there's no learning. The next 4 have some learning, but they're not particularly beneficial. And then the last 2, there's actually beneficial learning. So we're going to ignore providence over here and jump to the assumption that word order matters, because in these approaches we've ignored the order of words. But as we know, sequence is really important in language. I would much rather be getting the top one than the bottom one. So how do we take sequence into account? Well, the oldest approach is going to be a recurrent neural network, or RNN. The way this works is you have x1 through xn, same as usual, where x1 is the first word all the way through to the end of the CV. And then instead of just getting an answer out, that is the aggregate of all of these, we're going to get an answer for each word. And then for the next word, we're going to take in context from the previous word. So that's why it's recurrent, and it's drawn with this loop that goes round to itself. But you can unroll it and think of it as the sequence where we put in word 1, we get an answer for the entire collection, but we've only looked at one word, so the answer's not that great. But we pass a value from that example onto the next word, and the next, and the next, and the next, so that by the time we get to the last word in the CV, theoretically we've got context of the entire CV when making that prediction. Now the problem is that at any given point, that in-between state can get overwritten. What this results in is the model losing context of words that happened far back in the sequence. And a CV has a fair number of words in it. So how can we solve this problem? Well, the first solution was something called an LSTM, or a long short-term memory. Basically, instead of having a single state that moves between words or states, we have 2 hidden states, a short-term and a long-term state. Now, you don't need to worry about the math, but basically the idea is that as a state comes in, we make a decision, given the input, do we need to remove something from our long-term memory? Then we look at our short-term memory and make a decision, do we need to move something from short-term memory into long-term memory? And then we make a decision on the word, and then we pass on that long-term and that short-term memory to the next state. But RNNs have this problem where you have to process a CV word by word. This results in really long training times. So enter the next solution. It's a transformer. This is a model based off of a paper by Google called Attention is All You Need. And there are several components to this that we're going to step through. So it's an encoder-decoder architecture. And it allows you to train on an entire sequence of words in a single step. So the way that it does this is through something called positional encoding. So what we've got here is several sine waves, and what you do is you take the sum of all of those sine waves at a given point, and because these sine waves are at different frequencies, the sum of those will give you a different value, which means that from that sum you can infer the position in the sequence. So this allows us to pass the entire sequence, because for each word in our sequence we give it a positional encoding as well as the value of that word, and that allows us to move on. So the next thing that is important to note with a transformer is something called a multi-head attention layer. So a multi-head attention layer is a stack of attention heads, and all that an attention head is a key, a value, and a query. And so what will happen is for each layer we will generate a key, a query and a value for each index in the sequence, or each word in the sequence. And then what will happen is in the first layer, we'll generate that key, that query, and that value. The key won't be used because there's nothing to query. There's no previous layer. But when we get to the next layer, we generate a new key, a new query, and a new value. And then what we'll do is we'll use that query and match it to the keys in the previous layer. And then we'll pull the value from the previous layer into this layer. So what that allows you to do is a word can have context of a different word from a previous layer. So what this results in is this attention table that we've got. So if we look at the word I, it will always relate to itself, so it's got a really high value. But then if we look at the word I and went, there's not a strong correlation. And I and went has not got a strong correlation. So that value will not be pulled across to the word I. But if we look at the words went and home, there's a strong correlation between the two. Now, this attention mechanism is really powerful and allows transformers to train really quickly, and also gives a solution to the vanishing gradient problem where we can have context of words that are really far apart. But it introduces a new problem, is the square matrix, where only half of it really carries information, but because of the structure of the network, we build out this really large space. So there's a trade-off for this accuracy in terms of model size and consequently the amount of time to train it. The other thing to note is that we're looking at a encoder-decoder architecture, like is on the right, where we're taking information, we compress it down, and then we uncompress it to a new space. So you can think of this as something like language translation, where we start in English, we compress it down, and then we explode back out to Afrikaans. But we're trying to do a classification problem, like is on the left, where we've got an input that we're trying to squash down into an answer. We've got a CV, which is represented by many words. We're trying to squash all of those words down into did the CV pass or fail. Fortunately, we can just grab the encoder out of a transformer. The most famous one at this point in time is BERT, but there are several other powerful ones. And what we can do is we can use that encoder without having to train it or change it, because Google's already done that for us. And all that we need to do is add our own classifier head on top of it. So we'll pass our CV into the encoder, it will compress it down, and then we'll train a network that can take that compressed representation and compress it all the way down to an answer for us. So if we're going to train this, we want to see something like this, where we've got a loss that will start really high because it's random. That loss quickly comes down to a low value, and also our training and our validation lines follow each other and are close together. Reversely, for accuracy, we're going to start off at practically random, 50-50 split, because we've got a true-false problem. And as we train, we want to see a rapid increase in accuracy that plateaus out and flattens out as our model becomes stable and sure of its answers that it's giving. So this is what we get. Now remember, we've got the same set of CVs. The only difference between these experiments is how we're splitting those CVs between what we train on and what we use to check that our model is actually learning something useful. Now, if we remember that plot that we were looking at, only the last two sort of follow that trend, and there they don't particularly follow it well. But at least there is learning happening and there is a useful answer that comes out of this. So again, we will ignore the warning signs and move on and say, well, let's try an alternative approach. So we've got a CV, and we want to pull out useful information about those CVs. So we'll pull out experience, and for experience, we want to know what is the position that was held, how long was that position held, and where was that position held. For education, we want to know what is the degree, and where was the degree obtained. And then for skills, we want to figure out what is the skill and how long has the skill been had. So if you were to do this, you would probably want to do something like this, where you get a CV, you use computer vision to split it up and pull out the blocks of text which are related to each other, and then put those blocks of text through a classifier and then write a whole bunch of logic to actually go and extract the useful information. That's a lot of work. The honest answer is just pay someone. So we've now got text. We're going to use that text and we're going to encode it the same way we did previously, because remember, we've gone and we've extracted a university, we've extracted a position, but those are still words. So we need a way to convert those words. We'll convert them the exact same way we did for the previous problem. And we'll build out a solution that looks like this, where we've got a CV that comes in, we extract text features and numeric features, and then we concatenate all of those features together, put that through a model that gives us a classification. So if we step through this whole workflow, what will happen is we've got our CV, we've extracted the text, such as the position that is held. We'll encode that, so we go from text to a numeric representation, that gives us a vector. Then the other thing that we've got for our position that was held is how long it was held for. Now, neural networks are really sensitive to large numbers, so we're going to normalize that so our numbers fall in the same range all of the time, 0 to 1. That's what the normalization does, and that normalization results in a single number. What we can then do is concatenate those two numbers together to give us a longer vector, and we can get a vector for each experience position that was held, each degree that was obtained, and each skill that's had. And we can pass each of those sequences of vectors into an LSTM to convert from a sequence of representations to a single value of yes, this candidate passed, or no, this candidate did not pass. So just a reminder, we want our loss to decrease rapidly, we want our accuracy to increase rapidly, we want both of them to plateau, indicating that they've reached a stable point, and we want our training and our validation lines to follow each other closely so that we know that our model deployed in the real world will give us a reliable answer. So if we look at this, this becomes even noisier and less sensible than the previous training that we looked at, where there are no clear answers and no clear training. The interesting thing to note, because we were using an LSTM, we spoke about that vanishing gradient problem, and that's what you're seeing in these two plots over here, where our line flattens out. It could also go simply to infinity and then our plot would just disappear. But basically what's happened is the gradient has disappeared and our model can't figure out what steps to take in order to improve its accuracy. So we see this plateau. So we've tried all of these different approaches and we're seeing the same recurring pattern. What's actually going on here? So what you're seeing over here is a plot of a feature. What you're looking at is this candidate associated with institutes that pass the test or fail the test? And what you're seeing is different splits of that data. Now remember that that feature is learned off of the training data. And so if I use different splits, those scores will be slightly different between those different splits. So in an ideal world, what we want is a clean separation, or at least a relatively clean separation, between passing and failing. And we also want our test data to match our train data. So we want the blue dots to be with the green dots. We want the orange dots to be with the red dots, and we want a clean separation between those two. Now, as we can see with this split, although not perfect, it's relatively clean. But with this split, it's just a complete mess. So if we think all the way back to the original methods which train really quickly, we already saw this pattern where model didn't have a strong influence, but data split did have a strong influence. So what's the takeaway from this? What do we learn? Well, the answer is you can use the most powerful tools in AI, but unless you've got clean data that is a good representation of the problem that you're trying to solve with distinguishable patterns, no matter how powerful your tool is, you're still going to wind up with a bad answer. Thank you.